Okay, so this is section 5.5, indefinite integrals and the substitution method. So as we said in class, this method is basically what this entire section is about, and we did a few examples in class. So you see here these few slides. I'm not going to go over them again because I already did with you in class, but these are the things, problems you will find on the PDF file that I'm going to be uploading together with this video lesson for section 5.5. So here we have theorem 6, which is the one about the substitution rule for evaluating indefinite integrals, which the characteristic on indefinite integrals is that you don't have given limits as a and b, lower limit and upper limit. So ideally, for us to solve this indefinite integrals, we would like to have the functions written in this format where you have a function multiplying a composite function, which is, what's a composite? A function composed by another one that's being substituted inside of it, times the derivative of that inside function. And so what are the three steps to evaluate an indefinite integral in this way? It's going to be first substituting u by the inside function, and then finding the derivative of that inside function, which we're going to call du, more than likely, most of the time. And then number two is integrate with respect to u. So you're letting u be the derivative of the inside function. I'm sorry, you're letting u be the inside function, you're letting du be the derivative of the inside function, and then you're using that u to rewrite the indefinite integral in terms of u. And then you're going to do the integration, do the evaluating the integral. Number three is going to be replacing again the u by the original value of u, which was the inside function, g of x in this case, if you look at over here where I'm pointing on the theorem. So that's basically the same three steps that I did for the previous two problems in the first two slides, and this problem right here in slide 4. So all I'm going to do is add more examples of the same thing. So example number 5 is actually going to be using the substitution rule, but in a type of different problem that we have not done in class. So this is, I'm going to write here like a definition, let's say. So it says when a power of x appears in the integrand is going to be the function that you're going to do the integration of, the antiderivative of. That is one less than the power of x appearing in the argument of a function then we want to integrate by substituting ing at the end for the higher power of x. So here is example number 5. So we have to do the integral, we have to evaluate the integral of x squared e raised to the x to the third dx. So how do we do this integral? Well, let's rewrite this a little bit. This x squared is multiplying times this. So all I'm going to do is send the e raised to the x to the third times x squared. So all I did is I flipped this 2, right? It's the exact same thing. And so according to what I just wrote here, this definition, we're going to let u be the x to the third. It says when a power of x appears in the integrand that is one less than the power of x appearing in the argument, then we want to integrate by substituting for the higher power of x. So we're going to take the expression that has the higher power of x, which is x to the third power, right? That's greater than x to the second power. So then we're going to let u be that x to the third power. Now, what's going to be du? What's going to be the derivative of x to the third? Well, that's going to be 3x to the second power, right? And since I'm doing the derivative of an expression that is written in terms of x's, I'm doing the derivative of x to the third with respect to dx, right? So you always have to put that after the derivative of x to the third. So now, if you recall from today, we said in the classroom that together the expression that you're letting u be equal to and the derivative of u are expressions that have to be explicitly shown in the integrand, in the function that you're going to be, or the functions you're going to be doing the integration of. The thing is, I do see the x to the third power here, right? That's the function that I'm letting u to be. But the derivative 3x squared, nowhere we see it here. So then we have to do something to compensate that. So what we're going to be doing is we're going to have to add the 3, well, the x squared, if you notice that, and let me highlight it, this one and this one, they're already there. So part of this derivative, it's already here. This x squared is part of the derivative of x to the third. The problem is the 3 is nowhere here. Okay, coefficient of 3 times something, it's not here. So then I need to do something to compensate and to be able to add that up in here. So the only way that we're going to be able to do that is probably going to be by multiplying on the outside of the integral by 1/3, inside of the integral, e raised to the x to the third times x squared times the 3 that I need to have, right? As a matter of fact, I think it would look way better. I just did it like this for you to see that x squared and the e raised to the x to the third, the x squared are these two things that were already there. This times 3 is just adding this piece of the derivative that I was missing. So let's put it like this, times 3x squared, and we just leave it in terms of dx right now. Now, you're going to do the following, 1/3, and then you're going to start replacing in terms of u everything that you know you have. So, sorry, this symbol every time comes out not the way that I want it. So, 1/3 times the integral of e raised to the x to the third. But what was x to the third? So if you notice x to the third, it's going to be this x to the third. It's this one that's right here. And what's x to the third? It's the same thing as u. So then you're going to replace e raised to the u times 3x squared. What's 3x squared? Let me get another highlighter. X squared is this piece of this derivative right here. Okay. So then we're going to rewrite this 3, that's this 3. And then the x squared is just going to be du. Okay, so as a matter of fact here, this one, this entire thing, I am able to replace it by this entire thing. And what's this entire thing? Du. So then you're going to rewrite here, instead of you writing 3x squared, you're going to put times du. Okay? You don't need the dx anymore, because if you look at, let me highlight this, all this, 3x squared dx is the same thing as du. So this du is replacing all this. So then now, so what I did here is the first step. Assign something to be u from here, a piece of this function to be u. Usually the function that is substituted into the other one. So probably we have e to the x, and in that e to the x, the x is replaced with x to the third. The derivative of this is 3x squared, because we were missing the 3. I compensated by multiplying at the top times 1 at the front times 1/3. and then adding the 3 in front of the x squared, also in terms of multiplication. So now the next thing you're going to do is do the integration. Bring down the 1/3. What's the integral of e to the u is itself? If you recall, the derivative of e to the x is, the antiderivative, I'm sorry, of e to the x is itself, e to the x. Not the derivative, the antiderivative. E to the x, and then we're supposed to just simply put plus e. So then this 1/3 is going to be multiplying times e, but what was x? This is, I put an x and this is u. Say you here. So what are you going to replace? Sorry, I put an x, I don't know why. What's going to be u replaced by? It's going to be replaced by x to the 3rd power. Because that was a u over here. And that's basically the answer. Pretty much it. So the same thing as we did. Okay, the next problem is going to be example number 6. And we have to evaluate the following integral. X square root of 2x plus 1 dx. First thing, you're going to let u be 2x plus 1. The derivative of u is going to be 2, and it's with respect to dx. So then, we're going to find 2 situations here. First, we can all clearly see that this is going to be u, and there's no issue about that. The issue is going to come with the derivative of u. The derivative of u is 2x, but here I just have dx. So I'm missing the 2. I only have this part. I need to compensate for that. That's not big issue in reality because you already know how to do that. 1x, the derivative of x, square root of 2x plus 1, and this 1/2 at the front allows me to put a times 2 dx, right? And now we can truly say that this is going to be du. So then this is going to be u, du. Second issue is, what do I do with this part, with x? I have nothing to replace x with. So then that expression you're going to use to replace x with in terms of u, it's going to come from u solving for x, this expression where I just put an arrow right here pointing downward. So u equals 2x plus 1. You're going to subtract the 1. U minus 1 equals 2x. You're going to divide by 2, both sides. And I'm going to rewrite, I'm going to flip it over, or transform it, right? Not transform it, reflect it, I'm sorry. So x equals u over 2 minus 1/2. All I did is I let this denominator be the denominator of each of these 2 numerators. So now that x can be replaced by this entire thing. And that's what I'll do. U over 2 minus 1/2 times, that's just the x, times the square root of u times, and this is going to be du, the dx. So all I did is I replaced this part, and this part. Okay, so now that you have that, would it be time to do the actual integration? Not yet. First, let's do algebra to fix this a little bit, to make it less complicated than it is. So you cannot combine these 2 terms inside of the parentheses because this one has a u, while the other 1/2 does not even have a variable. But what you can do is distribute this u to the 1/2. U over 2 times u to the 1/2. Imagine that this u to the 1/2 has a 1 at the bottom, and that's going to allow you to multiply fraction times a fraction. So u is raised to the 1st power plus 1u. Every time you multiply 2 variables together, the variables are like variables, they're the same, you add the exponents. That's a basic rule for exponents. 2 times 1 at the bottom is a simple 2, minus 1 times u to the 1/2, it's u to the 1/2, over 2 times this one again is a 2. du. Let's simplify it again. So that's going to be u raised to the 3/2 over 2 minus u to the 1/2 over 2. Could we try now doing the, sorry that I went all the way to the bottom. Could we do the integration? Maybe, yes, but before you even do the integration, let's do something else that I know that's going to help. Rewrite the fractions as there's a 1 here at the front, we all know that, 1/2 times u raised to the 3/2 minus, there's a 1 here, so 1/2 raised to the, times u raised to the 1/2 du. Now, you can try to do the integration. So then you're gonna, at this point, I'm gonna do here a dotted line, and this is where you start doing the integration, just for you to see the difference in where we change from doing simple algebra to simplify and simplify and simplify as much as possible, and then the integration. So then the integration of this is going to be the 1/2, keep it as a constant. Use the power function for the antiderivative of this expression. U raised to the 3/2 plus 1, you add 1 to the exponent, over the addition of the original exponent plus 1 again, minus the 1/2 that was already there. Do the same rule for this part. U raised to the 1/2 plus 1 over 1/2 plus 1. At this point, I don't need the du anymore because I have already done the antiderivative or the integration of this using the formula. All I need to do here is add a plus d because when you're doing the indefinite integral of an expression or function, if there's no limit, that's why it's called indefinite, then you have to put a plus d. So 1/2, and then all we're going to do is basic algebra here, trying to simplify this up. So 3/2 plus 1 is going to be 5/2. Also, my denominator here is going to be 5/2 minus the 1/2 times 3/2 over another 3/2. Close the bracket, plus d. So then here, 1/2 times 1/2. What you can do here to simplify this, these u's have a 1 at the front of them. That's their coefficient. Imagine there's a 1 here, and what you're going to do is divide these two fractions. So 1 times 2, and whatever you get from there is multiplying times the 1/2, right? That was already there at the front. So that's going to be 2 over 5 u to the 5/2 minus 1/2 times, same idea or same concept, so 2 over 3 u to the 3/2. Let's see, 1/2 times, this is going to be 1 times 2 is 2, 2 times 5 is 10, so you have 2 over 5, 2/5, but 2/5 can be reduced to 1/10, u raised to the 5/2, minus 1 times 2 is going to be 2, 2 times 3 is going to be 6, 2, 6, but 2, 6 can be replaced to 1 over 3, okay, by dividing by 2, u to the 3/2 plus the c. Next, you're going to say, okay, 1/2. So basically the next thing is going to be distributing the 1/2. Actually, you're ready to do it because you simplify as much as possible this. So you're going to do 1/2 times this fraction and 1/2 times this fraction. So 1 over, I do something here. When I multiply this 2, this was supposed to give me a 2. When I multiply this 2, was supposed to give me a 10. So if you simplify 2 over 10, here it simplifies to 1 over 5, right? So this should have been a 5 right here. Sorry, half of 10 is 5. So tiny turtle mistake. So 1 over 10, right? 1 times 1, 1, 2 times 5 is 10. You keep your u raised to the 5/2 minus 1 times 1 is 1, 2 times 3 is 6, u raised to the 3 halves plus c. 1/10 times 2x plus 1, raised to the 5 halves, minus 1/6 times 2x plus 1. So once you simplify as much as you could the substitution of the u, then you just replace u by the actual value of u, right, from the given by the original inside function. And that's what our answer is supposed to be. So this is it. This is the final answer for the indefinite integral of this function. Quite lengthy, not impossible to do, but yes, you need to take your time and do it slowly because it's very easy to do a careless mistake. It's the same idea as all the other problems, just a little bit of more work. So next problem, it's going to be, where's my toolbar? Over here. So one more page. This is going to be example 7. Yep, example 7. And this will be this one. Evaluate the integral of 2z dz over the cube root of z squared plus 1. Okay. So I guess the first thing to do is let's rewrite this a little bit. That may help to see it in a different way. So this is how it's going to be. Let's rewrite it in terms of u again, as always, right? So who's going to be u and what's going to be the derivative of that u that you choose? U will always have to be a function that is inside of another one. So z squared plus 1 is inside of the cube root function. So z squared plus 1 du is going to be the derivative of this, which is 2z dz. Right? Don't forget to write it like that, dz. So then, can we use substitution directly without much work as the previous problem, where there were several situations there that we needed to take care of before plugging in the u's? I guess we could do it. Du is the numerator. 2z dz is du. The denominator is going to be written as the cube root of u, basically. So then, what if we rewrite this a little bit as u, well, first I guess, let me do it to the side so that we don't take that much space. Because I'm just rewriting after all. I'm not going to yet integrate. So this can be rewritten as du over, not the cube root, but let's rewrite this as a rational exponent, where you write it as raised to the 1 over 3. The 1 is right here, the 3 is the one outside. This could be rewritten one more time as, what if I send this u to the 1/3 to the top of the fraction, to the numerator? Well, now, and I know this looks as a 0, that it's supposed to be a u. I almost closed it entirely. That makes it look as a 0. So if I put this u to the 3rd to the top, the sign of the exponent will change to be negative. So then you're going to have u, I'm going to write it first, raised to the negative 1 over 3 du. So then, okay, now I guess we use basic algebra to rewrite it, to make it look in a way that it would be easier for us to do the integral of. So then, in the next step, that's where you really start doing the integral. The integral of this simple u raised to the negative 1/3 is going to be adding 1 to the exponent and dividing by this entire exponent. And whatever you do to this, plus c. So then, u raised to the negative 1 over 3 plus 1. 1 is 3/3. Negative 1/3 plus 3/3 is going to be 2/3. Negative 1/3 plus the 3/3 again in here is going to be 2/3, right? The same thing. So now let's simplify this before bringing in what u is equal to. Imagine again this is a 1, you put it over 1. The 1 in front of the u, you put it over 1. So that's going to be 1 times 3 is 3, 1 times 2 is 2, times u raised to the 2 over 3, plus the c. Now you can bring what the u is supposed to be equal to. We go back to the very beginning, u is supposed to be z squared plus 1. So you put here z squared plus 1 raised to the 2/3 plus c. And that's it. That would be the entire simplification for this. Okay. That's that problem. Then next problem is going to be example number 8. So for example number 8, we need to be aware that this problem is going to be about this. Sometimes we can use trigonometric identities to transform integrals that we do not know how to evaluate into ones we can evaluate using the substitution rule. Obviously, like you know, this whole section is about that. Substitution rule. So, what's the problem gonna look like? You have, for example, sine square x dx. So I need to find an antiderivative for this. If I go back to, let me see if this shows. If it doesn't, I'll open it directly from my MATLAB. Okay, it's going in the book. So in section 4.8, that is where the rules for the antiderivatives are located. So if I go back to section 4.8, specifically to page, I'm going to be the first page obviously. Not that one either, this one. Look through all the formulas and let's try to find something that says sine square x and find an antiderivative for that in the second column. There's sine, but there's no sine square x or sine square of anything, right? There's no sine square. So you can see that in section 4.8 that antiderivative doesn't exist or a formula for that. So due to this, you need to find what it says up here. Use trigonometric identities. These trigonometric identities are always provided for you on the formula sheets you get for every test. All you need to do is, on the test, get the formula sheet and look for something that could be a replacement for that. So why don't you use this formula? Which this formula is called, so this formula comes from the power reducing type of identities. Identity or formula. So I'm going to replace this by that. not doing the integration. This is just a replacement. This is not a formula for an antiderivative. I'm not saying this is the antiderivative of sine squared x. The antiderivative directly, there's no such formula for doing the antiderivative or the integration of that based on a formula. That's why I'm trying to find a way to rewrite it so that then I can do the integration of that. So if we rewrite this a little bit, we're going to see that we could rewrite, there's 1 minus cosine of 2x here, right? So I'm going to do the following. With another color, I'm going to put this in parentheses. Imagine there's a 1 here at the front, and this 1 and this 2, what I'm going to do is I'm going to take them to the front of the derivative in the next step, the derivative of the integral in the next step. So 1 and 2 are not there anymore. I took them outside together. Imagine I'm able to grab them from here, and I use them to form a fraction right here outside. So then what am I left with inside, or after the, for me to integrate? 1 minus cosine 2x dx right here. We just do it to make it simpler. So this 1/2 that was multiplying, the only reason that I was able to do this is because I'm saying this 1/2 is multiplying times this expression. If it was adding, subtracting, you cannot take a 1/2 that is adding to this expression outside, or 1/2 minus something, you cannot put it at the front. That would be wrong, only because it's multiplication. So then do the integration, but only of this part after the integral. Leave this one here, and then let's try to do the integral of this. So there's formulas for this, okay? You would have to say, okay, what's the integral for 1x? What's the integral for minus cosine of 2x? Well, it's going to be, if I go back, where was it? Over here. I'm going to look for cosine of 2x. Okay, there's a minus. I already know there's a minus here. That's this one. But cosine of 2x, is there a formula? Yes, right here, formula number 3. Cosine of kx, cosine of 2x, k is a 2. 1 over k, so 1 over 2 in my case, sine of 2x plus c. So then here, minus 1 over 2, that's 1 over k, times sine of kx of 2x. I don't need this dx because I already did the antiderivative, or I already did the integral. So now all I have left to do is distribute. 1/2 times x, 1/2. 1/2 times negative 1/2, negative 1/4, sine 2x. Plus c. What else could we do? Not much. Probably the only thing you could do is say 1 times x is x over 2. Here, instead of having the minus 1/4, minus sine 2x over 4 plus c. But in reality, to me, either this answer or this answer, both are correct answers. On a multiple choice test, as you always have, I mean, it depends what kind of problem you have, right? But there will be this kind of problems in this section where you have to use trigonometric identities to be able to integrate a function, because there's not going to be such a formula for that. For doing it directly, no. And here we really did not even have to use the U process, replacing everything in terms of U's, because the only way to solve this was through the substitution of this formula, the power reducing, and that took care of it itself. I don't need to do the replacement method of the use, okay, the substitution method. I mean, I substituted something, but not use. It wasn't necessary. At the end, the book also has, in this section, but not in 4.8, in the section we're going over right now, 5.5, they have this right here, this set of formulas or identities, or not identities, but set of formulas for integration. Show them to you, not here. It's actually right here. So the integrals of cotangent x, cosecant x are found in a way similar to those using used for finding the integrals of tangent x, secant x in example 7, C and AB. Next is okay. We summarize the results. Okay, so this one that you see here, let me, with my toolbar being open, this, I'm going to put them in the next slide. You may need them. I don't know if on the online homework there may be problems where you need this, but here it is in case you do. Couldn't find any problem on the actual textbook where you would use them, but it's just a matter of seeing if you need. For example, if I go back to section 4.8, so that was part of 5.5, what I just copied and put it in my PowerPoint, in my presentation. If I go to 4.8, and I'm going to go back again here. Look at this formula. The integral for tangent x, or let's say the antiderivative for tangent x, okay, is going to be, if you go here like this first column, look what it says on this table. Read it. Function, function. This is the general antiderivative, the second function, or the integration, let's say. There's formulas for integrating certain types of functions. These are 1 through 13. These functions have a formula to do the integration of them. The problem with this one, tangent of x, do you see on the function column, whether 1 through 7 or 8 through 13, do you see tangent of x somewhere? Not really. So tangent of x, what's the only way to integrate it? This. If you're going to integrate it by changing this into natural log of the absolute value of secant of x plus c. If you want to do the integration of cotangent x, you're not going to find it here. Cotangent, not here either. Secant x or cosecant x, not here either in the first column. So I'm going to copy also this one, and I'm going to leave it here just for you to see, like, okay, these are all the possible ways or all the different formulas that I could use. Plus, now you know that some problems are going to require for you to use identities, trigonometric identities, because that would be the only way to solve them. But basically, if you have something that doesn't have a formula from here that you could use, maybe it's one from this one. If it is a trigonometric function that it's not here, maybe use this one, or maybe use a trigonometric identity, actually. So just letting it there, food for thought, in case you have a problem like that on a quiz or on a homework. Okay, and that pretty much concludes this section. Okay, so this was section 5.5. I repeat again, indefinite integrals by using the substitution rule, and so this is it.